Bitmap and halftone concepts review. Bitmap measurement. The term spatial resolution refers to the concentration of pixels within space. In order to measure such a thing, pixels have to exist not within a file, but within a physical space, such as on a display. So when we measure pixels per inch, or PPI, we're measuring how many pixels for that specific display can be spaced linearly across the inch. Pixels per inch is dependent upon the display resolution, with more pixels per inch for higher resolution displays. Bitmap measurement, tonal resolution. So tonal resolution refers to the number of bits assigned to each pixel within the file. If a bitmap file contains 1 bit per pixel, it's only able to communicate 2 conditions to the computer, either on, which would be white, or off, which would be black. Thus, you end up with a high contrast tonal map. 8-bit tonal resolutions allow for 256 different numerical values that the computer can display as 256 different tones for each pixel. And then we have 24-bit images, which in reality are 3 8-bit grayscales, which the computer represents as a red grayscale, a green grayscale, and a blue grayscale, one layered over the other with light. A bit on bits. The binary numerical system is a numerical system that can be used in much the way we use our Arabic system. Our Arabic system is what we learn from the time we're in grade school. The binary system is ideal as a numerical system for computers because it's based on and off conditions. So a byte is composed of these sets of 8, and depending on the order in which those bits are on or off, a numerical value is represented. And again, in the case of 8 bits, 256 different numerical values can be represented. So when we deal with 3 grayscale channels, one for red, green, and blue, we're dealing with an enormous number of combinations, which then represent color values. The number of combinations can be found by multiplying 256 times 256 times 256, equaling 16.7 million combinations. You can see represented here a single pixel, which has a tonal value from red, a 132 from green, and a 234 from blue. And when superimposed on the display at those illumination values, this purple color results. This all relates back to channels in Photoshop, which Photoshop refers to as modes. A bitmap mode is composed of a 1-bit bitmap. The grayscale mode is also a bitmap, but with each pixel represented by 8 bits. Then we have the RGB, which we've just discussed. And finally, there's a 4-channel CMYK for print images. Those 4 channels equal 32 bits. So a CMYK image is a 32-bit image, 8 times 4. Now we'll talk about physical images on a substrate versus images illuminated with pixels on a display. The halftone has 5 characteristics, and we'll discuss each of these 5 characteristics now. Modulation is the type of halftone dot. There are 2 types, amplitude modulated and frequency modulated. Amplitude modulated dots vary in size depending on the tone. So relative size being a large dot in a given area being a dark tone, and a small dot in the same area being a light tone. This is the most common type of dot in traditional print processes like flexography and offset lithography. Frequency modulated halftone screens are made up of a single size dot within a given area, which are concentrated in higher amounts in the shadow areas and are very sparse in the highlight areas. Frequency modulated halftones are sometimes referred to as stochastic screening and dithered screening. Regardless of the modulation, a given area will have a dot area percentage. To measure this, an area is selected, usually a very tiny area, and in that tiny area, we measure how much of that area is covered with ink versus paper. For example, this area is covered 5% with ink, so it's a 5% dot, whereas this area is 80% covered with ink, 20% paper, and therefore is an 80% dot. We have instruments that will measure dot area, and this becomes an extremely important quality component when controlling tones with print processes. The dot area can be composed into scales called grayscales, or tonal scales. The tonal scale I have here is broken into steps of 10%. A tonal scale can further be broken down into what are called quarter tones, midtones, and three-quarter tones. At the whitest white, we have the highlight, and at the darkest black, we have the shadow. A synonymous term is white point, and on the shadow end, black point. Typically, quarter tones go up to 25%, the midtones from 25 to 75%, and the three-quarter tones from 75% up. The next characteristic of halftone screens is halftone resolution, and this is measured in lines per inch, or LPI. You can see here, this very coarse resolution halftone is 10 lines per inch. So lining up over an inch, 10 lines, the dots are aligned on those lines. When we get up to higher lines per inch, the dots disappear. But we still have, in this case, 133 lines per inch. An interesting point is that dot area is exclusive from lines per inch. In other words, a specific area, such as this 20% dot in a 40 LPI, is the same dot area as these smaller dots, represented in 100 LPI. Again, 20% of the area covered with ink and 80% with paper. With regard to dot area and screen frequency, or LPI, we have a very important quality characteristic called TVI, or tone value increase, also called dot gain. There are a variety of reasons that dots grow when printing, depending on the print process, but they do grow. Mechanical gain is from pressure between the plate and the substrate. Optical gain is the spreading of the ink into the substrate around the edges of the dot. Regardless, the higher the LPI, the higher the dot gain, or again, TVI, same term. This is an important relationship, and measuring the dot gain is essential to controlling the tones in the print process. Then we have dot angles, with black at 45 degrees, the least visible angle, and then magenta and cyan at 30-degree increments from black. 45 add 30, 75, 75 add 30, 105. These 30-degree increments form what's called a rosette, and a rosette is a type of moire pattern that you can see represented by these circles. Any screen at an angle other than 30% will give us an unpleasant moire. Yellow is used between 75 and 105, that is 15 degrees, because it's not visible, yellow being very hard to see, so your eye won't pick up the unpleasant interference patterns. Here's an example from a clothing catalog of fabric details in the image interfering with the screens. This is referred to as an image moire and is usually discovered during printing and can be a very expensive discovery. This requires changing the angle artificially at the rip so that the moire pattern created disappears. Frequency modulated screening will not create these moire patterns. FM screening is most common on inkjet printing devices and many laser printers. Finally, we have dot shape, which refers only to AM screening. Note that with round dots, all of the dots connect in the three-quarter tone simultaneously, right about this area here. That creates a rough tonal jump that creates an unpleasant line in the three-quarter tones. The same thing happens in the square area, where all four corners meet simultaneously, creating dot gain that results in a sharp, harsh tonal jump. The elliptical dot is the most common dot, used in 99% of AM screens. The reason being that tonal jump where the dots connect happen in two spots, once here and once further down the tonal scale when the opposite edge of the ellipse begins to touch, thus minimizing the tonal jump.